So we said that the electron energy and its position are complementary. We can't know both at the same time. The energy of an electron can be described as 1/2 times the mass times the velocity squared. So for an electron with a given amount of energy, the best we can do is to describe its position in terms of what we call an orbital, which is a region in which there's a likelihood that the electron will be found. So orbital is different from an orbit in the Bohr model, but it is still a place where the electron is most likely to be found. We find that many of the properties of atoms are related to the energies of the electrons. And so the energy of the electron tends to be more important to us than its position, because the energy of the electrons in an atom affect the behavior of the atoms, and that's what we care about. The atom is too small to see. The electron is way smaller than that, so the exact position of it in the atom really just doesn't matter that much. So we focus on the energy. So Schrödinger worked on this, besides thinking about cats and killing cats in boxes and stuff. So Schrödinger's equation allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. Here's a very this is deceptively simple appearance of Schrödinger's equation. It's actually some very, very complicated math that thankfully we don't have to go into. To solve Schrödinger's equation, you get a bunch of wave functions that describe the wave-like nature of the electron. And if you plot those wave functions squared, that gives you a shape that represents an orbital. So when we do these calculations, we end up with some integer values being plugged into the wave equations. And these are necessary to quantize the energy, because we know from the emission spectra of different elements that the energies of the electrons are quantized. And so the wave function also has to be quantized. And so we introduce integers to quantize that. So those integers are called quantum numbers. There's the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and a fourth one called the spin quantum number. And these are given symbols N, L, M sub L, and M sub S. The principal quantum number corresponds to the energy levels, or those orbits, in the Bohr model. So there was the orbit 1 and orbit 2 and orbit 3, and as you went up in the orbits, you had higher and higher energy. And so this principal quantum number corresponds to that. The principal quantum number is an integer, and it can be 1, 2, 3, 4, 5, etc. It can't be 0. It can't be negative. The larger that number is, the higher the energy of the electron, and the larger the orbital size. We can calculate some of these things for hydrogen. For hydrogen, we can calculate that the energy of an electron is equal to negative 2.18 times 10 minus 18th joules times 1 over n squared. So you can plug in n equals 1, n equals 2, n equals 3, and you can calculate the energy of that electron. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. Negative energy is more stable. Higher energy, higher positive energy is more unstable. So as n gets larger, and we look at the difference between levels, the difference in energy between the orbitals gets smaller and smaller. So here we can look at principal energy levels. So principal quantum number 1 We can calculate the energy of the electron for level 2. We can calculate the energy level 3, level 4. And what we observe is that as you go from 1 to 2 and 2 to 3 and 3 to 4, the difference gets smaller and smaller. And that continues to get smaller as you go out. And it's a function of the exact equation there. So this is higher in energy. This number is less negative than this one. These are higher in energy. They're less stable. The angular momentum quantum number describes the shape of an orbital. And this can have integer values from 0 up to 1 less than whatever n is. And these have letters associated with them. And this is for historical reasons. So when L equals 0, we call that S. And L equals 1 is P, L equals 2 is D, and L equals 3 is F. Seems kind of random. Why didn't we choose A, B, C, D? That would have made more sense. These letter designations come from descriptions of the line spectra. So I always forget what S is. P is principal, D is diffuse, F is fine. And I just really can never remember. You can go back and listen to all my old lectures. Every single semester I say I can't remember what S is. Anyway, so we use these letter designations a lot, and they correspond to 0, 1, 2, 3 for that angular momentum number. The magnetic quantum number specifies the orientation of the orbital in three-dimensional space, how that orbital is aligned relative to other orbitals, and the values for that range from minus L to plus L, including 0. So if we look at how many m sub L values there are, that tells us how many orbitals of a particular shape there are. So if L equals 2, L equals 2, 0, 1, 2, SPD, that's known as a D. Then the possible levels for m sub L, or the possible values, range from negative L to positive L. Well, if L is 2, then m sub L could be minus 2, it could be minus 1, it could be 0, it could be plus 1, it could be plus 2. That's what we mean by m sub L can be minus L to plus L, including 0. So there's 5 different values. There are 5 different orbitals with the same energy when L equals 2. The spin quantum number specifies the spin of the electron. Spin is a fundamental property of the electron. It's not the same as a top spinning clockwise or counterclockwise, but it's easy to think of it that way, and that's good enough. So you can think of, I don't know if you guys ever played with Beyblades. There's the tops that spin counterclockwise and ones that spin clockwise, right? So electrons can have a positive or a negative spin, and it's like the Beyblade spinning in different directions. The value is equal, they're just opposite spin. So we talk about plus or minus, spin up or spin down. So a specific combination of the first 3 quantum numbers describes one orbital. So we could say, well, n equals 1, L equals 0, and m sub L equals 0. That describes an orbital. That describes what's known as the 1s orbital. If the n values are the same for several different orbitals, We say they're in the same principal energy level or the same principal shell. And so we have levels and we have sublevels. If the values of N and L are the same, then we have a sublevel or a subshell. And I would expect at this point that you are thoroughly confused and overwhelmed by all the letters and numbers. So if you are, have hope, it's normal at this point. Because it's just a lot to get your mind around. Here's an illustration which hopefully will help us to begin understanding what's going on here. So if N is equal to 1, that's the first principal energy level, the lowest energy, the most stable. When N equals 1, there's only one possible value for L, because L can be 0 up to 1 less than whatever N is. Since N is 1, 1 less than N is 0. So L is 0, that's it. That's called S. And so we have 1 orbital there because M sub L also has to be 0. Level 2, principal level 2, now we can have L equals 0 or we can have L equals 1. When L equals 0, M sub L has to be 0. It's the only option. That's the 2s orbital. When L equals 1, now M sub L can be from minus L up to plus L. So it can be minus 1, 0, or plus 1. So then there's 3 orbitals there. On the third level, we've got same situation with L equals 0. There's only one possibility. L equals 1, now we've got 3 different orbitals. L equals 2, now M sub L can be minus 2, minus 1, 0, plus 1, plus 2. There's 5 different orbitals. Yes?
So the value of N states how many numbers below it the L's are? I don't know how to say that, but
The values, the possible values of L and M sub L depend on the previous quantum numbers. So the principal quantum number determines how many or what the values of L can be. So when N is 3, then we have 3 different possibilities for L, 0, 1, or 2. When N is 2, we have 2 possibilities. When N is 1, there's only 1 possibility.
you can't go below 0 for L.
Can't go below 0.
So if N was 4, then
You-
we have 4 possibilities.
Yes.
Being 3, 2, 1, 0.
Yes. Yeah. When N is 4, you can have L equal 0, 1, 2, or 3. 4 possibilities. And if you have L equals to 3, then you've got more possibilities for M sub L. Minus 3, minus 2, minus 1, 0, 1, 2, and 3. 7. Okay? I like this picture, so I'm going to give you a preview. This reminds me of a very strange hotel. So here we have the 1, 2, 3, etc. These are like the floors of the hotel. The first floor, the second floor, the third floor. And each of these represents a room. So on the third floor, there are 3 rooms. On the second floor, there are 2 rooms. On the first floor, there's 1 room. These orbitals remind me of beds. So the S orbital has, the S sublevel has 1 bed in it, one orbital. The P has 3 orbitals or 3 beds. D has 5 beds. That helps me see this, gives me a picture of this. I'll elaborate more on that later.
So we're just going to have to remember that it's S, P, D, F.
You just have to remember S, P, D, and F. Yes, I'm sorry. Okay, so let's do this one. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? I don't think it's nice or useful to grill you on quantum numbers, But we do need to talk about them because we have to understand how they structure the atom. So if we've got 5D, that 5 tells me that the principal quantum number is 5. And D tells me I've got 0, 1, 2, 3, L equals 0, L equals 1, 2, 3, S, P, D, F. So the fact that this is 5D tells me that M sub L is 2. I'm sorry, L is 2. So N is 5, L equals 2. And then what are the possible values for M sub L? They go from minus L to plus L, right? So we could have minus 2, minus 1, 0, 1, and 2. So there are 5 different orbitals. And they're identified by their quantum numbers. We've got 5, 2, and negative 2. 5, 2, and negative 1. 5, 2, and 0. 5, 2, and positive 1. 5, 2, and positive 2. So each orbital has its own combination of quantum numbers. So the quantum numbers sort of act like a social security number. They identify, right? Each set of quantum numbers is supposed to specify an orbital, but there's a mistake in each of them. Replace the one that's not allowed with one that is allowed. So here, n equals 3. Can n equal 3? Sure it can. Then if n is 3, can L be 3? It can only go up to 1 less than n. Right? It starts at 0, 1, 2. So L cannot be 3. Okay, so that one's wrong. We need to choose between 0, 1, or 2. But then we need to choose something that'll work with this last one. There's only one mistake. If M sub L is 2, that forces our decision about what L is. It has to be 2. These aren't possible if M sub L is 2. Because when I have L equals 2, M sub L could be negative 2, negative 1, 0, 1, or 2. So let's look at this one. N equals 2. Okay, we could do that. L equals 1. Does that work with N equals 2? Yeah. L equals 1. Can M sub L be minus 2? No. What are the limits here? Negative 1, 0, or 1. Right? From minus L through 0 up to plus L. Now you could choose any one of those, and that would be correct. How about this one? N equals 1, L equals 1. Does that work? No. What does L have to be there? 0. And then can M sub L be 0? Yeah, it has to be. Yes?
I don't understand how you're getting both. In this case, it's 0, and then like previously, can't be 0, can't be 1, it's got to be 2. Are you looking for numbers that are, I guess, smaller than the n?
So for L, the number has to be smaller than n.
Okay.
This one, we couldn't do 0 or 1 because we're also told that the next one is plus 2.
What's that under then?
So M sub L can be from minus L to plus L. So if L equals 0, then M sub L has to be 0. If L equals 1, then there's 3 possibilities for M sub L, minus 1, 0, and plus 1. If L equals 2, M sub L can be from minus 2 up to plus 2. So it can be minus 2, minus 1, 0, 1, or 2. So as this gets larger, we get more possibilities here. So we were told that M sub L was 2 for this orbital. So if M sub L is 2, then L must be 2. Because if L was 1, M sub L can't be 2.
If M sub L was 1, it wouldn't be able to be 2. Yeah, makes sense.
Well, if M sub L is 1, L can be 1. But we're told that M sub L is 2. We got this. And so then we're trying to figure out which one of these is possible. Well, only this one.
Yeah.
Yeah. So that's why we can't have 0 or 1 here.
Alright. Oh, yeah, okay. So, it's just all the zeros and ones.
I know there's lots of 0s and 1s.
It makes sense.
Okay.
Would there ever be a case if M sub L was unknown?
Well,
We just choose a normal.
it turns out that the actual value of M sub L doesn't really matter that much. It's more how many values are there that matters.
Can you go back real quick?
Yeah.
I just want to copy it down.
Okay, so let's see how this explains atomic spectroscopy. So each of the lines that we see, each wavelength, corresponds to an electron transition between 2 different orbitals. When an atom absorbs energy, an electron goes to a higher energy orbital, we say it's excited, because, when you've got extra energy, you're excited. The excited state is unstable, and eventually the electron will relax down to a lower energy orbital. When it does that, it releases the energy difference as a photon of light. And so that photon, the energy of the photon, corresponds to the difference between those 2 orbital energy levels. Here it is in a diagram. So here we've got an electron in the first principal energy level. It absorbs energy and jumps up to the 3rd level. It's not stable up there, so eventually it's going to relax down to a lower level. It may go directly down to the 1st level. It could go to the 2nd level and then later go down to the 1st level. All of those transitions are possible. When it goes from 3 to 2, it releases the energy, and that energy is given off as a photon of light. In order for an electron to go to a higher energy state, it has to get exactly the right amount of energy. Exact change on the bus. That if you've got too much, they won't let you on. Seems weird, but if you've got too much energy, you can't go to that level because there's nothing that can be done with the extra. So the electron will absorb the energy that is needed for the next to a higher level. Has to be just the right amount. Electrons in high energy states are unstable. They tend to lose energy and go to lower ones. And those the lines in the spectrum correspond to differences in energy between energy states. So the wavelengths of those lines give us information about these energy states in the atoms. So we can predict the spectrum for hydrogen. Hydrogen is a nice simple atom. It only has 1 electron. So we can predict the wavelengths by calculating the difference in energy between 2 states. For an electron in energy state for an electron in energy state n, there are n-1 energy states it can transition to. Therefore, you can get n-1 lines. Both the Bohr model and the quantum mechanical model predict the lines very well for hydrogen. We can calculate the difference in the energy. The difference in energy is the final energy minus the initial energy. And so you can calculate the energy of the final state based on the principal quantum number and the energy of the initial, and you can subtract those, and you can simplify it like this. The energy of the energy change of the atom is opposite in sign to the energy change of the photon, because the photon leaves the atom, and so one's negative, one's positive. Wavelength is hc over energy, E. So here's hydrogen, n equals 1, 2, 3, 4, 5, etc. If you go up to n equals infinite, that's the same as ejecting an electron. It leaves the building, it's left the atom. So we see these transitions. These are the ones that fall in the visible region. It's going from 5 to 2, 4 to 2, and 3 to 2. And we're going to be looking at these when we do experiment 7a. These transitions, the energy changes less, and so those correspond to infrared wavelengths. We can't see those. These transitions are higher in energy, and they correspond to ultraviolet radiation, and we can't see those either. So these are the three lines that we see. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So we need this equation. This guy right here. The change in energy is equal to minus 2.18 times 10 to the minus 18 joules times the difference between 1 over the final n squared minus 1 over the initial n squared. That's going to give us the change in energy, and that amount of energy is what's released or absorbed, and we can calculate the wavelength using this. So, delta E, negative 2.18, it is minus 18? Okay, thank you. 1 over the final squared minus 1 over the initial squared. So, we're talking about light being absorbed. It's going from n equals 2 to n equals 7. So this is my final, and this is my initial. So my final n is 7, so 1 over 7 squared minus 1 over 2 squared. So negative 2.18 times 10 to the minus 18 times the quantity, parentheses, 1 over 7 squared minus 1 over 2 squared. Close the parentheses. The energy there is 5.01 times 10 to the minus 19 joules. This came out to be a positive number because the atom is absorbing energy. It's gaining energy, so this is a positive. The wavelength hc over E. So Planck's constant, that would be given 6.626 times 10 to the minus 31 joule seconds. Speed of light also would be given 3 times 10 to the 8th meters per second. And energy, we just calculated 5.01 times 10 to the minus 19 joules. This one we can see the units working out nicely. The joules cancel, the seconds cancel. We're going to end up with a wavelength in meters.
Planck's constant up to the -31st, which is -34.
I think it's, yeah, you're right, it's 34. Thank you. 31 was the mass of the electron. 6.626 times 10 to the minus 34 times 3 times 10 to the 10th, sorry, 8th. I was thinking centimeters. That's what I came up with. That's the wavelength of light. For hydrogen, a transition between n equals 2 and n equals 7. You can convert that into nanometers, and you're going to get 397 nanometers. Any questions?